Okay, if you remember at the beginning of the course, when we started Unit 1, I said that it was broken down into two main categories. Well, we're done with the first category. The first category, if you recall, was kinematics. And kinematics referred to being able to observe and describe motion. And you learned 3 or 4 different formulas to help us calculate and be able to describe the type of motion that's happening, whether it is velocity, whether it's accelerating or decelerating, what's happening to the motion. So we can describe that. The second half of the unit I said was falling under the category called dynamics. And dynamics refers to how does it move. So now we're actually going to look at all of the things that cause motion in the first place and then come back and relate it to the calculations that we learned in the first part of the unit. So in order for anything to move at all, we have to deal with forces. So a force, it can be a push or a pull, and this is also a vector quantity. Remember, if we have a vector quantity, it means that there's a direction associated with it. And that sort of makes sense because if we're pushing or pulling something, we can also say what direction we're doing that in. So for each type of force, we're going to learn about different types of forces. There are letters that they've come up with to help represent what forces we're talking about. So for instance, just a general force, we give and we're going to write these down for each one. So for just a general force, we use a capital F. And because it's a vector quantity, we put that little half arrow on top. Okay, now we're going to look at the different types of forces that exist. So there's two main categories. First category is non-contact forces, meaning that these are forces that happen at a distance. So one thing you can probably relate to would be something like an electrical force. So we know that a positive and a negative force of attraction attract each other, right? A positively charged something and a negatively charged something will attract. If we have two of the same charges, they repel. So those are examples of forces. Another is magnetic, right? If we stick a magnet's north end near a south end, they're going to attract. But if we put two north ends near each other or two south ends, they're going to force each other apart. And we can feel this attraction and repulsion without actually touching them together. So that's what I mean by non-contact. So the main one we're going to deal with here is the force of gravity as being our non-contact force. So first of all, we use subscripts now to talk about the different types of forces. So gravity has a little subscript G. Okay, so the force of gravity is represented by this symbol, and it's the attraction between all objects, but we only notice it when the object's really huge. So for example, we talked about the force of gravity on Earth earlier in this unit. And we feel the force of gravity. It's what holds us on this earth, and it's what holds everything around you that you see on the surface that it's resting on. Now, this definition says it's the attraction between all objects. This is true. There is actually a force of gravity between you and every other object in this room. But we don't notice it unless one object is incredibly huge or a lot larger than the other. So that's why Earth's, if you look at how huge Earth is in comparison to us and all the objects on it, that's why all of the things are pulled and you can feel that force. Okay, so the next category we're looking at now, contact forces, things that are in contact with each other, what type of forces exist. So the first one I want to look at is something that a lot of people get confused. It's something we call the normal force. Let's first define what symbol we're going to use. So capital F, and it's usually, I think your textbook uses a capital N. It could be a lowercase n too, that's fine. This force exists for anything that is resting on another object. Okay, so it has to be on the surface of something. And this force is basically responsible for the reason why things can rest on top of an object. So for instance, a ball sitting on top of a desk, or a computer sitting on a desk, or your table that's resting on the floor. Everything that's in contact with a surface and it's just sitting on that surface, there's a normal force that balances out gravity. So we know the reason it's resting on the surface is because gravity's pulling it down. Well, it helps to explain why doesn't your computer fall right through your desk, or why if you're sitting on a chair, do you not fall right through that chair? because of this normal force. It balances out gravity. So the reason you're sitting on your chair is because gravity's pulling you on it. But why don't you fall through it? Because of this normal force that we don't see, it's balancing. It's equal and opposite to your gravity. And that's why you rest on top of something. Okay, next force. We're going to look at these in a little bit more detail to help kind of put a real life situation to them. So next force is friction. This is the force between all objects in contact. So in order to show this, we're going to use F and a little lowercase f to represent friction. Now there's 3 different types you can have, and you guys can relate to these. Kinetic represents moving. Kinetic, anytime you see this word, refers to something that's moving. So if you think about, let's push a desk across the floor. You know that it's difficult because if that desk is heavy, it's going to create a contact force between the bottom of the desk and the floor, and you have to overcome that contact with the friction of the floor. Okay, so that's for anything that's moving. Now, static is the same thing, but we're just looking at something that's stationary to begin with, and we want to try and get it to move. It has, so anything in contact with anything else has a certain degree of friction. It's sort of like a stickiness that is created between those 2 surfaces. So I'll give you an example you can think of. If you were to take your desk and try and push it across the floor that it's sitting on, it would be tough, and you'd have to use quite a bit of force to overcome the friction that exists between the floor and the desk. If you were to take that same desk and put it on an ice rink and try and push it, you're going to have a lot easier time. You'd need less force to push it because there's less friction between those 2 surfaces. Now, the only difference between kinetic and static is that kinetic is once you're already moving, there's still friction that exists, but in order to get it moving, you have to overcome, there's still that friction that exists before it starts moving. So that's the only difference between kinetic and static. So static means not moving. Okay, and then the final one, anything that's traveling through the air, even though we don't see those air molecules, there are particles that exist, gases, right? Oxygen, carbon dioxide, nitrogen in our atmosphere. Anything that travels through air experiences resistance with that air, right? It's a friction that's moving in the opposite direction to what you're trying to move. So that's something actually we might want to add. It always acts in the opposite direction of motion. So it kind of makes sense when you think of friction, it's working against what we're trying to do. So if you're moving through the air, the friction of the air molecules is the force that those air molecules put on something that's moving. And if it's moving to the right, those air molecules' friction is moving to the left. So it always opposes the motion that we're actually moving. Okay, I think that's it. Oh, and last one, tension force. Anything that's attached to a string, a rope, a chain, any other thing that's attached to something and you're pulling it with something or you're hanging it, because there's tons of different examples here, we call that tension force. So it's our last force, capital F, and we use a capital T to represent tension. Okay, so now that we know what symbols represent each of the following forces, next thing we kind of want to know is, well, how do we measure force? Okay, so that's the next thing we're going to look at. So I'm going to post a little video on what a Newton is and how it was discovered. It's named after a famous scientist called Isaac Newton, who helped to come up with the law of gravity and the properties of it. But so a Newton is basically a unit that we use to measure force. And if you recall, I'm going to give you an example you might be able to relate to. We talked about gravity, and gravity is what pulls us down towards the center of the earth. So that's a force. So when we talk about our mass versus our weight, so let's just look at these examples. Our mass is the amount of matter in an object. So let's even just use us as an example. We have a certain mass, and it's measured in kilograms. Now, this amount of matter that we have, let's say it's 50 kilograms. This is just the amount of matter that our body's made up of. This never changes, no matter where you are. You can increase it by gaining weight, but your mass is something that just tells you how much matter you're made up of. If we talk about our weight, what we're actually referring to is the force of gravity on our mass. So on Earth, and so it's measured in newtons, or a newton is the same thing as saying a kilogram times a meter, the acceleration of gravity. That's the same thing as our weight. So our weight on Earth is actually just our mass times whatever gravity is. So when we think about our weight, I know we usually hop on a scale and we measure ourselves in pounds or kilograms, but scientifically, our weight is actually a force because of the force of gravity, and it's measured in something called newtons. So if we wanted to figure out what our weight is, so our weight in general terms is really the force of gravity on our mass. So our weight is equal to our mass in kilograms times the force of gravity. Now remember, the acceleration due to gravity is a constant number, and it's always 9.8 meters per second squared. This, when you substitute, if you know what your mass is in kilograms, it's that amount times 9.8, and your final units are in newtons. So in science class, when we talk about our weight, we're talking about our force of gravity in newtons. I know in everyday life we talk about our weight in pounds, but scientifically, the definition of weight is just taking your mass and multiplying it by 9.8. Okay, so the unit that we use in letter for a newton is a capital N. Okay, just one additional thing. Some of the questions you're going to work on in this part of the unit are going to want to take your weight. And so just use an estimate. You don't have to know exactly how much you weigh, but a lot of you probably know what your weight is in pounds. So if you know your weight in pounds, you can't use pounds when you're trying to figure out newtons, because it has to be a kilogram per meters times meters per second squared. So you have to know what your weight is in kilograms. So just if you want an estimate, if you know your weight in pounds, so take your weight in pounds and divide that amount by 2.2. And that's going to tell you what your weight is in kilograms. So some of the questions when they ask you to approximate your weight, you don't have to use your own weight. Just pick a weight that represents an average person, divide it by 2.2, you get your weight in kilograms, and then you can put it into this formula to figure out that force. So anytime they use the word weight or force of gravity, that's what we're talking about. Okay. Now we want to know how to draw diagrams that represent all the forces acting on an object. And so this is something called free body diagrams. A free body diagram shows all the forces acting on an object, and we use a dot to represent the object and vector lines to represent the forces. We're just going to look at 3 examples, and I think you'll get the hang of it. So our first example, a fish on a fishing line. You have to think about all the forces that might be acting on it. Now, if we're on the Earth, which most examples are going to be on Earth, we always know that there's gravity acting. So there's going to be gravity hanging and pulling this fish down. But because there's this there's this line here that's hooking onto this fish, we know that there's another force pulling in the up direction, which is the tension force. So all a free body diagram is we use a dot to represent our fish, or our object, in this case it's the fish. And you should use a ruler for these types of things. We use, let's just see how to do that, to show our force going up. No, this isn't a straight line. Give me 1 second. So because it's a vector, we want to use a straight line with an arrow on it. So we know that there is one going up, representing tension, and gravity's acting straight down. And they're balanced, so they should be approximately the same length. The same length represents the same amount of force, right? If this thing is just hanging there and it's not moving, it means the tension force up is balanced by the gravity force down. And all you have to do is label this up force as our tension, our down force as our gravity. And that is a free body diagram that represents our fish. Let's look at a couple more examples. A ball resting on a desk. So remember, anything that's resting on the surface of something, remember up here our fish wasn't resting on any surface, it was hanging. If you're resting on the surface of something, you automatically have gravity pulling it down. But because this ball isn't falling through the desk, there must be a balanced force in the up direction, and that's that normal force. So if our ball is our object, we represent with a dot. We know gravity's pulling it down. And because it's balanced and it's not falling through the desk, we have an equal and opposite force up. We label each force, so force of normal. So our normal force is up, our gravity force is down, and this ball is not moving, so these are the only forces representing this free body diagram. Okay, and our final example, if we wanted to push a desk across the floor, let's say we're going to push it to the right. That's one force. So if they don't specify a certain force and they just say we're going to push something or we're going to pull something, we have a general term for that, and I'll show you. So our desk is our object, and if we're going to push it in a certain direction, and I said we're going to push it to the right, there's a general form we use, or general thing we use to represent this type of force. We just call it the applied force because it's general. We're applying some sort of push or pull force. So we use an F with an APP to represent applied, meaning that we've applied some sort of force. It's just a general push or pull. So we're pushing that desk to the right. Now, gravity's holding it on the ground, so there's got to be a force in this direction. And because it's resting on the floor, it's not falling through the floor, there must also be a balanced force going up. And because it's in contact with the floor and we're pushing it in this direction, there's going to be friction that opposes that motion in the opposite direction. So we have to represent all of these on our diagram. So we have our applied force to push it to the right. We have a normal force that's balanced out with gravity. And we have a frictional force working against us trying to move it. Now, our frictional force is probably going to be a little bit less than our applied force, so we'll make that smaller. And how do I know that? Because if we're successfully moving it across the floor, this force has to be bigger because it's overcome the frictional force. So we're going to label this as our normal force, our gravitational force, and our frictional force. So all you need to do when you're asked to draw a free body diagram is think about all the forces that might be involved in each situation. If you have any object resting on a surface, you're always going to have gravity and you're always going to have that balanced normal force. The only time you don't have a normal force is when you're not resting on an object. So if you're flying through the air, or if you have something hanging from a rope like we had with our fish. Okay, and that's it. So I'm going to give you some practice questions to help practice drawing free body diagrams. If you want to check anything with me or you're not sure about something, please email me, because what I've been doing, people who have been emailing me questions about some of the practice questions that I leave, I will either make a video to try and help explain what it is, or I'll draw it out for you and send that to you for extra help. So keep checking. I will also post those in the discussion for everybody to see. So when you ask for help, most often I'm going to post my answer to that question for everyone to see. Okay, so keep checking there as well, and please don't hesitate to ask for help.